Unfortunately, the video died, but that's okay. For number 3, I was saying how you could very easily find average speed of the point right now, but careful, because what I asked for is to double the frequency and then find the average speed. So what I'm going to do is I'm going to draw in double the frequency. If you have more waves per second, then you're squishing in more waves in the same amount of time. So instead of 1 wave right here, you would get 2 waves right here. Or you could think about it as right here, the period is 0.4 seconds. If I double the frequency, that's going to mean half the period because they're the inverses of each other. So now my new period is 0.2 seconds, the new period. Now, when I'm asking you to find average speed, well, average speed is V equals C over T. A lot of people want to use the period, totally fine. You can do, okay, it goes up 10, down 10, down another 10, up 10. That goes 40 meters in 0.2 seconds. That's going to give me 200 meters per second. But you don't have to use the period. You have a bunch of different times here. You can use 0.1 right here. It goes up 10, down 10. That would be going 20 meters in 0.1 seconds, which is, again, 200. Or you could just say, oh, up to 10, that's going to be 0.1 seconds. So it does 10 meters in 0.1 seconds. So that's going to be, that's 0.05, not 0.1, sorry. 0.05 seconds, so that's going to give me 200 as well. Biggest thing here is remember to actually double the frequency. So if you get 100, that's the average speed of the wave right now, not with double the frequency. 4, we've got a generator, oscillates the frequency that can be adjusted. The other end of the string is pulled over with a pulled over a pulley with a hanging mass. They adjust the frequency until a standing wave with 1 node is created, or 1 antinode, sorry. Would look something like this. And then they measure that frequency that creates that as F. As the student moves the generator now so that the string is twice as long, now your generator's over here, we want to know what frequency will she need to create a standing wave with 1 antinode. So you actually still want to make the exact same shape as before. So if I'm making the same shape with a longer string, what we've changed is the wavelength. So now you have a greater wavelength. Because right now, at first, the wavelength was just 2 times the length of the string, and then now the wavelength is 2 times the length of the string, but your string is 2 times longer, so you have 2 times the wavelength. You have not changed the tension, you have not changed the medium, so you have the same velocity because it's the same medium. If you look at V equals F wavelength, if you double the wavelength and you keep this the same, that means that you're halving the frequency, because halving and doubling will cancel out, so you need 1/2 the original frequency from before. Now, just in an extension, so you hopefully, just to help you understand more, that was only because I kept the exact same antinode with twice the distance. I actually could have kept the same wavelength if I had created a wave with 2 antinodes like this. So if I create 2 antinodes with twice the length, that's actually the exact same wavelength as before, so you would need the same frequency to create that. Number 5, a student is sitting on the edge of a swimming pool and repeatedly dips their foot in and out, making waves across the water. The student dips slowly at first and then starts doing it faster each time to the same depth. So first I'm going to pull out, this is the same depth. The depth is like the amplitude, the displacement from equilibrium, so I know this is the same because it has the same depth. And I also know that wave energy depends on amplitude, so this would be the same. And our reasoning being because it's at the same depth and energy depends on amplitude. The other thing that I know is going to be the same is the wave velocity, because wave velocity depends on the medium and we have not changed the medium. Still in the swimming pool, so unless the temperature of the swimming pool significantly changed during this time, the wave speed will be the same. Now let's talk about what it is that you are actually changing. If you're dipping slowly at first and now you're doing it at a faster rate, you're doing more dips per second, so you're sending more waves per second, which means you're increasing the frequency. Because you're sending more dips or more waves, literally, per second, which is the definition of frequency, the waves per second. Now your period is inversely proportional to the to the frequency, because period is just 1 over frequency, so if I increase frequency, that means you're decreasing the period. You could also think if you're doing more dips per second, there's less time between dips, so less time for each dip. and your wavelength. So let's think about our equation for wave velocity, because I know what happened to my frequency. I increased it. I know that this stayed the same, so that means the wavelength had to decrease, because increasing and decreasing will multiply to keep the same velocity. So this one had to decrease to keep the same velocity. Alright, number 6, 2 wave pulses are created simultaneously at opposite ends of the string, and they move towards the center of the string as shown. They have the same width, and these are possible shapes at different moments in time. Which of the following shows the correct time order of the pulse as it moves along? So obviously this is like the beginning. So figure B is my first figure, which is all of my answer choices, so I can't cross off anything here. Let's talk about after they overlap, because overlap is obviously going to be tricky. It's like one of these. After they overlap, they'll now be on the opposite side of one another. So this one will now be going this way, and this one will now be going this way. So figure E is definitely my last picture. So we can at least cross off answer choices that don't have figure E at the end. So we're now 50-50 shot, even if you don't know what they look like overlapped. Now, when you're overlapping, you have this one, and then you also have like the triangle right here. Now, the string is not going to go both up and down at the same time. So what's going to happen is you're going to have like this minus, or I guess this one minus this one. It doesn't matter which one. I'm going to do like the bigger minus the smaller. So I'm going to have this one right here, but I'm going to take away this triangle. So this triangle does not exist anymore. And then see what's left is this right here. If I had a pencil, I would show you like literally you can do this and then take away that triangle, and then what's left is this shape right here. Figure C is what you would get if you had the triangle and the, like this, going towards each other, because that would be constructive interference. Figure D is what you would get if you have like this one and the triangle down, because see how the triangle is taken out of this. So basically, these two are flips of each other. It's just that the square part is the one that's down here. So A is the correct one, which means that your answer choice is C. Number 7, a ringing bell is located in a sealed chamber. When the air is pumped out of the chamber, you're taking away the air, so you're taking away the medium. So the bell is actually not going to be heard, because sound needs a medium in order for its energy to transfer the energy. So what's happening when the bell rings, my bell, it's causing the molecules in the bell, obviously, to go side to side, which would cause the air molecules next to it to go side to side, which causes the air molecules next to them to go side to side, until the air molecules next to your ear are going side to side, and your eardrum will like interpret that. But if there's no air molecules, then it's just the bell that is going side to side. They're not hitting any air molecules, so that energy can't be transferred. Number 8, we have a representation of a wave at a given instant in time. So this is like literally the physical wave. Is it a longitudinal or transverse? So this is longitudinal, because you'll notice that the oscillation is going to be side to side as the wave is going this way. So you're not, like, there's no displacement up, down, or like anything perpendicular to the wave going this way. The individual points are either moving like to the side, left, or right. Can we tell the wavelength? Yes, absolutely. It is the distance from compression to the next compression. So the same way for this wave, it would just be from crest to crest, or etc. You can say from here to here is one wavelength. Or if you're looking at like 2, 2, 2, I would have to actually count. I think it's this one right here. 2 over here, that would be a wavelength. That would be like kind of like from trough to trough. Or you can even do equilibrium to equilibrium. Equilibrium is somewhere between the really spread out, the rarefactions, and the really compressed compression. So like this would be an equilibrium, and here would be an equilibrium. Can you tell the amplitude? Kind of. I can't give you a number. But you can tell the amplitude, because you can say like, oh, this is squished together. If you had another wave, like if I were to draw a wave with a bigger amplitude, it would look like this, and then like really spread out on the rarefactions, etc. So remember, amplitude is displacement from equilibrium, so you can kind of see what equilibrium is like, and you can see the difference between how spread out this is and how spread out equilibrium is, or how compressed this is. Now, I can't actually give you a number, but yes, you can tell amplitude just like qualitatively, like this one would have a greater amplitude than that, etc. Can you tell frequency? No, you know nothing about the frequency because you have no time dependence, right? So I have nothing that depends on time. I can't tell period, I can't tell frequency, I don't know the velocity. All I know is what the wave looks like at a given instant in time. So I can say amplitude and the wavelength from this picture, but I have nothing to do with time and no velocity, so I can't find the frequency. Number 9, so two wave pulses are approaching each other, which shows the shape of the resultant. So you're going to have this one on top of like this. So if you think about, at this point they're going to add, at this point they're going to subtract. So here you've got this one with another one on top, and at this point you've got like the right half of the square with this one on bottom. So this is going to cancel out, and this is going to make just a bigger one, which would be A. Hopefully those drawings helped. Remember, it's not when like this part hits, right? It's when their centers are overlapped. So it's this one right here. So this is going to add and these cancel out. Student hits the tuning fork lightly taps it, and here's a note. She taps it harder. What changes? So if you're hitting it harder, you're giving it a greater displacement. You're going to make it louder, which is increasing the volume, which is talking about like the amplitude. So basically all this is saying, oh wow, that does not look like words, volume. You can pause and go back, hear what I was saying when I wrote it. This is basically saying it's getting louder. So you have a greater amplitude, so the maximum displacement of the tuning fork has increased. When you hit it harder, all you are changing is the amplitude. You're not changing the frequency. The frequency would literally be like the rate or like how many oscillations it's doing a second. That's not what you're changing. So this should stay the same. If your frequency stays the same, your period should stay the same. The wave speed, so how fast the sound wave is going to travel, is not going to change because you're in the same medium as before. Your wavelength, if your wave speed and your frequency is the same, wavelength is going to stay the same. All you've changed is the amplitude. So that's not going to, the amplitude does not affect these. So amplitude has no effect on those four. Now the average speed of a point on the tuning fork, well, if this is your tuning fork and at first it was going like this, side to side, so not a good picture. If it's going side to side like a millimeter, what was it, like a 288 times a second, and now it's going 2 millimeters. This is like you hit it really, really hard. It's going back and forth 2 millimeters, 288 times every second. Then you've increased the average speed because it's going, or it's oscillating a greater distance in the same period of time. So if you were to look at your V equals D over T, right, we've increased the distance and kept the same time, so that's going to give you a greater velocity. Number 11, two wave pulses interfere and they have a displacement, they have a displacement of amplitude 0.3 when they overlap. Which of the following are possible values of the amplitude? So you could have 1 and 0.2. Totally, that makes sense. That would give you a resulting amplitude of 0.3. I could have 0.3 and 0.3. So those would come together. That would give me an amplitude of 0.6, which is not the case. Or I could have 0.3 and then 0.3 the opposite way. Those coming together would give me a flat line, amplitude 0. So B is not going to work, whether they're in the same direction or opposites. You could have 0.6 and 0.9. If those come together, that would be 5, which is not correct. If I have 0.6 and 0.9 opposite directions, then they would subtract and they would, they would create an amplitude of 0.3. So this is possible. 0.3 and 0.9, if they were in the same direction, like both up or both down, doesn't matter, that would create 1.2. If they were in opposite directions, whatever one was up or down, doesn't matter. Their resulting amplitude would be 0.6, so D would not work. Number 12, we got the transverse wave traveling on a string. The graph shows the position as a function of time for a point on the string. What other piece of information would you need in order to calculate the wave speed? So let's think about wave speed is v equals f wavelength. From this graph, I can get the amplitude, right, the maximum displacement of this point. So I know the amplitude is 3. I can get the frequency. Remember, definition of frequency is the time for one wave. So, or sorry, not time for one wave, that's a period, is the number of waves per second. I have 1 second, that's 1, 2, 3, 4. So your frequency is 4 hertz. And then period is the time for one wave. You could say, oh, that would be here, that's half of 0.5, which is 0.25, or you can do whatever frequency. So I have amplitude, frequency, period. I want to find velocity. Well, that means that I know this one, so the only thing that I need is the wavelength. Sketching the interference of these two waves when they meet at several different positions, so right before they meet. So let's call this like point P. Then at point P right here, you would have this box and this triangle. Looks like they're the same width, so as they start to interfere, not when their centers overlap, so just at the beginning, that would be like I have the box and then I have the triangle like this, and they're like the same amplitude, so I'll fix that. Let's say something like this. Well, that means that this part of the triangle is on top of this box, so I'm going to shift that part of the triangle up like that. So then the like this. Now that might look really weird, but if you think about it, it's just I have the box and I have this part of the triangle that's just shifted over, that's normal. It's just that the other part of the triangle got shifted up like this. So this part of the triangle is just shifted to make the whole triangle as before. Centers overlap should be easy because you have this with the triangle on top, so I'm just going to add it up like this. It should look like a house. Oh wow, I didn't start to draw one. I started to draw it like a real house. Ignore that part right here. The rope would not be doing that. And then when their centers overlap, after their centers overlap, but they're still interfering, so now the triangle is like on the other side. So I'm going to draw it where I've got like this. One half of the triangle is off, but then the other half of the triangle that would be right here has been shifted up on top of this box because they are constructively interfering. So it would look so weird to draw. It looks so funky. And then after they pass through each other, it should be easy. They're not going this way. And anytime they're, like, wherever the wave pulses are not, the string should be flat because they're not carrying energy in those parts of the wave right now. 14, a fifth harmonic standing wave is created on a string of length L. What is the wavelength? So this is one wave. And I meant to say in terms of L, by the way. So one way to do this is you could say, okay, L is 5 loops. 2 of those 5 loops make the wavelength, so that's 2/5 of the length would be your wavelength. Some of you counted up how many waves you have. So you have 1 full one, 2 full ones, 2.5. So you have 2.5 waves in a length L. So the length of one wave would just be L over 2.5, which is 5 halves, which gets flipped over to 2/5. Figure below shows a wave traveling on a string. The arrows indicate the direction of velocity at certain points at a particular instant in time. Is it transverse or longitudinal? Transverse, because the wave is either going to the right or to the left. We don't know yet, but the oscillation is up and down, which is perpendicular to the wave direction, so that's going to be transverse. Now the next question, which direction is the wave propagating? Is it going to the right or to the left? I will say that these 2 points right here aren't going to help you, because if the wave was shifting to the right, if the wave was shifting to the left, this point would next be up, and this point would next be down. Or if it was shifting the opposite way, either way, this one is going to go up and this one is going to go down. So you have to look at these ones in particular, because these ones will do the same thing no matter which way it's going. Now if you look at this one, in order for it to go down, that's on the left side, which means that the point, remember the point isn't what moves, it's the wave energy that moves. So in order for the wave for this point to next go down, that means the wave is shifted over to the right. So if you sketch the next part not the next part, if it was shifting to the right, what it would look like. See how this point would now be up here? See how this point would now be up here? This point would now be down here. This point would now be down here. This point would now be down here. So all of these check out. So that means that the wave is moving to the right. Now if you're saying here, wait, but on the left side it's down, that's totally true because that part has not reached it. It would need to be moving to the right for this down energy to reach the next point. 16, a generator oscillates with one end of a string at a frequency, can be adjusted, pulled over, blah, blah, blah. They repeat the process for several harmonics, keeping the same hanging mass at the start. So same hanging mass means same tension, which means same velocity. So your wave speed should be constant the whole time if you're keeping the same string at the same tension. And they want to calculate the speed of the wave. So speed of the wave is v equals f wavelength. So basically that means you need the frequency and you need the wavelength. Amplitude has nothing to do with the speed of the wave, so that's not going to be helpful. The mass, like the measuring the hanging mass, it doesn't matter because as long as the tension is the same, the velocity will be the same. Frequency of the oscillator, absolutely. The number of waves in each harmonic. So we're going to create a first harmonic, we're going to create a second harmonic, you're going to create a third harmonic, etc., all at the same length of string. Just counting the number of waves doesn't actually give me my wavelength, right? You would also need to know the length of the string, so you need both B and C. These two together will be used to find wavelength. Because you can say like, oh, this right here, 2 notes, that's one wavelength, but unless you know the length of that string, you don't know the wavelength. If you know that this is, well, I don't know, 10 meters, then you're like, oh, this is wavelength of 20, this is wavelength of 10, this is 2/3 of 10, etc. Number 17, we have 2 standing wave patterns. They're produced by holding a vibrating fork. What is the relationship between wavelength A and wavelength B? So first of all, this is saying wavelength B in terms of wavelength A. So let's just figure out which one's bigger and which one's smaller. Remember, length of the wave, not how many waves. So this is definitely a longer wavelength, and this is definitely a shorter wavelength. Because here, I've got one wave right here. For this one, I only have 1/4 of the wave. The full wave would be like way off the paper over here. So much longer wavelength, much shorter wavelength. So we can cross off anything that says that wavelength B is not shorter. This is saying wavelength B is 3 times longer than A. Definitely not, it's shorter. So we can cross off anything that is not saying wavelength B is shorter than A. So it can either be 1/3 of A, 2/5 of A, or 1/5 of A. So now we have to actually count out how many waves. So right here, I have 1/4 of a wave. Here I have a full wave and a fourth. So think about it, if you're thinking about it in terms of fourths, I've got 5/4 of a wave. So if I'm fitting 5 times as many waves into this same length as this one, then that means each wave is 1/5 shorter. Or you could actually calculate the length of this one would be 4 times L, whereas this one would be 4/5 L. So that means that wavelength B, this would be wavelength A, wavelength B is literally 1/5 of the original one. 1/5 of wavelength A. Ice cream truck is in the parked on the road playing its tune, sending out sound waves, etc. You've got a kid standing in line, you've got a car approaching, meaning it's going towards, and a biker going away. If it's going towards, then because it's coming to meet each of these sound waves, this is a terrible picture of sound waves, because it's coming towards them, these are going to seem squished together. It'll seem like a higher frequency for the car. The kid, it will seem normal because they're just coming at a speed. He's not going towards or away from it. If you're going away, then you're getting farther away from each wave front because you're traveling with the wave, so that's going to seem like a lower frequency. So talking about time between successive wave fronts. Time between successive wave fronts, well, the time between waves is just a period, right? The time for one wave until the next one. So this is going to be higher frequency will be a smaller period, less time, and a lower frequency will be a longer period. So this is going from least to greatest because these signs mean that it's bigger on the right side, smaller on the left side. Hopefully I didn't need to say that. could review if I did, that's fine. So then the smallest period would be the car, then the kid, and then the longest period would be the bike. So car, kid, bike. And then frequency, well, higher, lower, normal. So the lower frequency would be the biker, then the kid would be normal, and C would be the higher frequency. So bike, kid, car, A. The only thing that can change the speed of the wave is the mediums. You can literally go to a different medium, like change from a rope to a skinny string, etc. Or that could be like within the same medium, you could change the tension of the rope or the string, or the temperature of the air, water, etc. that you're moving through. Two students are sitting next to each other, and one gets really excited, starts talking with a higher pitch. That is a higher frequency. So that's a shorter period, a shorter wavelength. The wave travels faster than before? No, the medium's the same. Amount of time between successive compressions is less. That's the period. You do have a smaller period. The molecules disturbed now undergo a greater displacement. That would be increasing the amplitude, which is like the volume, not the pitch, not what I'm saying. Areas of compression are now spaced out farther from one another. That would be a longer wavelength. I said it's a shorter wavelength, so not that one. Ashley takes a 3-meter rope and adjusts the frequency, shakes the rope up and down so she creates a standing wave. Then she cuts some length off the rope and starts oscillating at the same frequency. Is it possible for her, using a shorter rope than before, to get the third harmonic? No, because if you're still a third harmonic, but you have a shorter length, then you just change the wavelength. So now you would have a shorter wavelength. You still have the same velocity, because it didn't say anything about her increasing the tension or changing rope, so it's the same medium, so you still have the same velocity. So you would need a, let me think about this, higher frequency. If this is the same, this decreases, yeah, you would need a higher frequency to create the third harmonic on a shorter rope, because that wavelength would decrease. Now the next question, probably got a couple of you guys. It says, is it possible for her to create any standing wave? Doesn't matter which harmonic. It doesn't have to be the third. Just any harmonic at this on this rope with a new frequency. And the answer is yes. Now, it's not like any length. It would have to be a very particular length. So let's think about if you have the same speed and you have the same frequency, that means you just would need to have the same wavelength, right? Well, right now, this is 3 meters. So this has a wavelength of 2 meters. Well, what if I cut my rope to 2 meters long? And I created a second harmonic. See how if this was 2 meter long rope, then I can have the same frequency. That's the exact same wavelength as before. I just have less of it because I have the right length of string. Or I could cut it to a 1 meter long rope. If this is 1 meter long, then I have half a wave. Half of that wavelength of 2 would be 1 meter long, and it would still be the same frequency and the same wavelength at the same speed. So yes, it is possible, and the best explanation is these examples. It's not going to work for any. If I cut it to 2.5 meters long, then it's not going to work. It'll get chaos. But it's possible to get standing waves with the same wavelength. You just have less of them. It just has to be the right length of rope. Standing waves are produced by a 100 hertz generator in a string of fixed length. The tension is increased, so that means that you have a faster speed. And it says same frequency. Yeah, it doesn't say anything about frequency, so same frequency. V equals F wavelength. If you increase this and keep this the same, then your wavelength would have to increase. So we can cross off these. Because tension varies directly, yeah, more tension is more wave speed, and then speed varies inversely with wavelength. No, more speed means more wavelength, so they both vary directly.
Mrs. Aceba's advisory, please report to Ms. Robinson's room upstairs. Mrs. Aceba's advisory, please report to Ms. Robinson's room.
Sorry, guys.
234.
Alright, last one, a string of fixed tension and linear mass density. is attached to a vibrating speaker. It is observed that a speaker frequency of 60 hertz does not produce standing waves. What is the explanation? Well, right, like not all frequencies will produce a standing wave for a certain length of string. It's totally possible that 60 hertz would produce a wavelength on a different length of string. Just kind of like what we were saying here, right? Whatever this frequency is, it works for a 3 meter long rope, it works for a 2 meter long rope, it works for a 1 meter long rope, but it wouldn't work for a 2.5 meter long rope. So what's happening here is you have to have the correct length of string for a certain frequency. If you have, this is fixed tension, so that means you have a constant velocity. And you have a constant frequency, so you just need the right wavelength. And in particular, for a string, right, it can look like this, or it can look like this, or it can look like this. Oops, that's how many, pretend that was 3 loops all the way. So basically, we can have as many, I'm almost done, number of loops as we want, but the length of this has to be like a multiple of a loop being 1/2 of a wavelength. So whatever your wavelength is that goes with this frequency and velocity, my length can only, it has to be a multiple of 1/2 of the wavelength. So in this one, our wavelength was 2 meters, and I could have 1 meter, 2 meter, 3 meter, 4 meter, because that just means one more loop, etc. Part B, the wave speed on the string is fixed. That is true, but that doesn't mean that you can't create a standing wave. Because if I had the right length and my speed was fixed, if I have the right length, it doesn't matter, I get a standing wave. I don't really know what that was talking about. And then wavelength produced is equal to the speed of the waves divided by 60. Yes, that is true. You just divide the speed over, but that would be true if I had a standing wave too. It's not why I don't have a standing wave. Okay. Sorry.